Good morning, people. This is lecture 13, and today is February 16, 2023. In about five hours, we'll have our test number 3 during the tutorial time later today. So instead of me doing anything new, this essentially short lecture, relatively short lecture, is devoted to a set of review problems that may help you for later today. Okay, so the first problem that we're doing situation is stated here. A machine part of mass 1.95 kilograms, so this mass 9.5 kilogram, vibrates in a viscous medium. Here's a viscous medium, oil or something like that. Determine the damping coefficient when a harmonic exciting force of 24.46 Newton results in a resonant amplitude of 1.27 centimeter with a period of zero point 0.2. So what it's saying is that you apply a harmonic load like that, and this F naught is 24.46. And what we get at resonance, the value of the amplitude of this vibration is 1.27, and the period of oscillation is zero point 0.2 seconds. Now, first of all, the fact that we have the period of oscillation here means that we have the frequency of oscillation. And let's go ahead and write down what we know for a damped harmonic motion. We have the solution of this equation written as big X. This is the amplitude, cosine of omega t. And this uh, 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 omega, actually this omega is associated with that period. In other words, uh, I might have said this is the damp period. That is not correct. What this is saying is that the omega leads into a period of zero point 0.2 seconds. Okay, so first of all, we know what x is. For a problem like that, we in earlier lecture we came up with the amplitude of this oscillation is equal to f naught over k times this. Okay, now omega, the frequency of oscillation of this mass, is 2 pi over the period of it. So 2 pi divided by 0.2, 0.2 is given here, and that is 10 pi. And if you put the pi in this, you get 31.415 radians per second. Now, what do we know here? We know F naught. Okay, we know F naught. We know R, because at resonance, R is 1. We know big X, okay? And uh, uh, let's see, let's move on. Yep, so at resonance R equal to omega n, that is 1. So the natural frequency is actually exactly the same number, okay? Because this ratio is 1, the natural frequency is exactly this number. We have the mass, we can find the K, okay? And K comes out to be 1925 newtons per meter. Now, what we want to do, of course, is we want the damping coefficient. We found the K. We want to find the damping coefficient. So now we use the fact that big X is 1.27 centimeter, and F naught, big F naught, is 24.46. Plug it in right there. At resonance, R is 1. Notice that this will disappear, and we have 2 zeta times R. R is 1. The only unknown here is zeta, and zeta is going to be 0.5. And this is the this is the damping ratio. And in case you want to find the C, let me see now, find the damping coefficient. Damping coefficient is C. So you write down the expression for C in terms of zeta and C critical. Remember, zeta is C over C critical. So you just write down C critical. This is one way of writing it. The other way of writing it is 2 mass times omega n. That's the other way of doing it. But either way, You have everything here. You have K and M is given to you 1.95, and zeta we just got, and you're going to get C equal to 61.3. So that is uh, first problem. Now, the only thing that could have caused the confusion is, well, when you read this thing carefully, actually it tells you that this period is associated with the frequency of oscillation of this, which is omega, incidentally. Steady state frequency is omega. Okay. Second problem. We have a 50 kilogram instrument. It's mounted on 4 springs. Each spring, the stiffness is given. If the foundation experiences a harmonic motion, so this is a base excitation problem where the motion of the base or the base or the ground is given as this. So this is y of t equal to that. What is the amplitude of vibration of the instrument? So this number in front of cosine, this is big Y, okay, big Y. This omega, this 50 is omega frequency of the oscillation of the base, okay? We called it omega B when we treated this thing. It means omega of the base, but you can drop the B if you want. We have the stiffness. So the mass we know, we want to find the big X. Basic excitation problems. This is the mother of all equation for basic excitation problems. There is also one for the transmitted force, but this is for amplitude. What we know is we know the big Y, we know R, or at least we're going to find R. Okay, R is omega of B. This is omega B. Okay, divided by omega N. We can find omega N because we have a stiffness, 4 of these, and the mass of 50 kilogram. So basically, we know R. And zeta is uh, zeta, we're gonna, oh, there is no damping here. You can see that there is no dampers. Obviously not in the drawing and not in the statement of the problem. So zeta is 0 basically. So let's plug it in. No damping, zeta equal to 0. Omega n natural frequency is K over M. M is 50 kilogram. K, there is 4 springs of this stiffness, 2 in the front, 2 in the back probably. Yep, so we got the omega n. And R is omega B over omega n. Omega B is this number inside of the cosine, 50t. This is omega B. Omega n we just calculated. So we have R approximately 2. So in this expression, remember zeta is 0. In this expression, the only thing that we don't know is let me see now. The only thing that we don't know is big X. Big Y, you're told is 0.002. You just plug in the stuff here and you get your big X, which is right there. This is meters, okay? So it's about 0.6 millimeters. Very good. And yep, that takes care of problem number 2. Uh, One thing you want to check here, and it's obvious when you do that, notice that R is 2. Okay, R is 2. If you plug in 2 in this expression without the absolute value, if you plug in R equal to 2, you get a negative number, which means big X is going to be a negative number. That minus sign simply means that the mass is 180 degrees out of phase with the base motion. Okay, that's just a comment. Now, here's another problem. As soon as you see this, you know that you better write things in terms of theta, okay? And you better take moments at some point about O. This is similar to the stuff that we did on the earlier test and stuff in the first 2 weeks of the course. Now we have a uniform bar. The mass of the bar is given. It's 10 kilogram. Pivoted at O, and at the 2 ends we have springs. Well, we have a spring here and we have a spring here. This spring connects the point that you see there to the ground. Think about a ceiling, ground, whatever. And this spring is between that point and the point where actually x of t, a harmonic displacement, is being applied. Okay, so the displacement, harmonic displacement, is applied to that point P. Similar to the case that we have base excitation here, except that it's not base excitation, it's just that we excite that point P with that kind of a displacement. All right, we have the stiffness of these two springs we know, and the damper we know, damping constant we know right there, and the frequency of oscillation omega right there is also given to us as 10 rad per second. And we know that the amplitude of this displacement oscillation, applied displacement pattern, is 0.1. What we want to do is find the steady state angular response of the vibration. Now notice that when you do this, this bar starts vibrating up and down and up and down. What you want to know is what is the maximum angular displacement when this bar goes up and down, hinge about that point. And that's really what uh, the maximum of this angle is going to be the amplitude of the oscillation of the angle theta. Okay? So one thing is for sure is that we have to write everything in terms of theta, and then take the moment of all forces about that point O. So let's start. Here's a free body diagram. Let's pretend that actually this is going up. Therefore, the spring, this spring on the left, it says no, no, no. So there's going to be a force vertically upward because the spring wants to limit the motion of this point, resist the motion of this point. The damper says no, 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 no. You can't come up. Therefore, there's a force of the damper which is trying to push this thing down. Okay, and then this spring on the right-hand side also exerts a downward, think about a downward displacement. Now, here's the situation. For example, let's pretend that this thing actually, uh, this, actually, this thing, this F spring, I drew it like that, but uh, this actually changes direction. So the direction of it, let's pretend that it's downward. Okay, even if you drew it upward and you solve the problem, you're going to come out to be okay at the end. So first of all, left spring is the stretching times the stiffness. The stretching, or in this case, stretching is just the theta times that length. See this arc, which is the amount of stretching. We're talking about small angle displacements, small angle oscillation. So this distance is almost L over 4, that length, times that angle theta, and then we multiply it by the stiffness of the spring, we get the force of the spring on the left side. The damper, is going to be C times this distance derivative of this distance. Remember, so well, before I do the damper, let's go ahead and look at the spring on this side. So uh, well, first of all, this point goes up, right? This point goes up, and the end of the rod also goes up by the amount theta times CL over 4. So the actual amount of stretching or compression is the difference between the x and 3L over 4 theta, because this point moves, point P moves, but that the point where the bar is located is also moving upward. Okay, therefore, what you see here, is the net stretching of the uh, of the uh, uh, spring on the right side, and you multiply it by K, okay, and you're going to get the force on the spring. Okay, now the one thing I want to make sure here, so we are assuming that this thing is actually a positive number, right? X of t bigger than that. That's why we talk about stretching of this. Now, as far as the damper goes, is just the c times velocity of this point. Now, what is the what is the velocity of this point? Isn't it r theta? R theta is that r theta is that distance. Now, when I say r, means L over 4 actually. L over 4, L over 4 times theta is going to be the displacement of this point right underneath that force. But we're interested in the derivative of that, velocity of that. So it's going to be L over 4 times theta dot. And then you multiply it by the damping coefficient, you're going to get the damper force. This is a reaction force at the R, at the pivot, which is, I'll call it R, but it's not going to come into the picture because we take the moment of all these things about the point O. Okay? Take the moment about the point O. I wrote these things for your convenience. Take some of all the moment about the point O in the counterclockwise direction, being positive. Okay? And if you just patiently go ahead through taking these forces and multiplying it by the moment arm, do not forget the moment arm. These things have to be multiplied by the moment arm. So the moment arm of this fellow is L over 4. The moment arm of this fellow is also L over 4. The moment arm of this fellow is 3L over 4. Okay. Now just be careful. Follow this convention that we're taking. Everything counterclockwise, all moment counterclockwise is positive. So when you do that, for example, this guy is going to give you a negative moment. This guy is going to give you a negative moment. And so is this one. This is going to give you a negative moment. Okay. And equal to J about O. J is the moment of inertia about the point O, pivot point, times theta double dot. Okay. Now to find J of O, if this was a rod, about its center, it would be ml squared over 12, right? ml squared over 12. But because we're talking about the point O, we have to take the parallel axis theorem. So the mass of the rod times the distance from the center of mass, which is exactly halfway in the bither, uh, to the point O squared. This is the parallel axis theorem. Just clean it up. You get this. And the x appears on the right hand side. You can see the x displacement appears on the right hand side. It was x naught times cosine of omega t. Remember, x naught cosine of omega t. There we are. The data is given to us. All the information is given to us. X naught given, omega is given. So m and k and c, etc. So all this thing, you plug it in, it translates into this stuff. Notice that this is the effective mass. Inman also calls it equivalent mass. This is the equivalent damping coefficient. This is the equivalent stiffness, or I call it effective mass, effective stiffness, and effective damping coefficient. And this is the amplitude of the oscillation, harmonic oscillation, F naught. Okay. Now, we have the solution to this thing. Please go ahead and look at your notes for solution to that, steady state solution to that, okay? Now, we didn't have theta, we had x double dot, x dot, and x. Every time you see an x, replace it with theta, okay? So when you do that, this formula that we have seen many, many times, it said big X equal to F naught over K, okay? Now, we don't have big X, it's everything in terms of theta, so it's big theta, the amplitude of oscillation, the amplitude of oscillation. That's exactly the thing that we want to actually calculate. That's the thing you want to calculate. You just plug in the values there. You need everything that you need. You get 0.03, 0.01311. This unit is wrong. This should be radians. Okay, this is wrong. This is not meter, radians. Okay. Uh, yeah, good. Now, what I have done here is this is the phase, by the way. This is the phase angle. This is the phase angle. Phase angle for this problem. This is the amplitude for this problem. But what I have also done, I've also plotted, although it didn't ask us to do it, I've also plotted it. First of all, wrote down the expression. The big amplitude, big theta is 0.01. Oops. Uh, this should be 0.01. Should be 0.01. Okay. Because let me see now. What did we input for? We are inputting meters. Okay, in meters. So uh, this is wrong. This should be 0.01, right? And then this is the phase angle right there. The phase angle right there. I've plotted this. This is a solution. I've also done the same thing, except that pretended that this thing was cosine, this was sine instead of cosine. So the solution, look, it's exactly the same thing, except for it's shifted. The right. So the red one that you see is the motion of that point P. This blue one is uh, the 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 angle as a function of t. Okay, here I've done exactly the same thing. Pretend that force is 0.01 sine of 10t instead of 0.01 cosine of 10t. Everything is switched to, all the numbers are going to stay the same, but this is going to be switched to sine. So notice that these two curves, this blue one and that blue one, are identical. And it's just that they're shifted by 90 degrees, basically. Okay, so this takes care of our problem number 3. Let's go to problem number 4. Read this thing. A centrifugal fan weighs that much, so we have the mass of it, and has a rotating unbalance of 20. Now remember, this 20 is not the unbalanced mass. It is the product of the unbalanced mass with the eccentricity with G. Okay? That's what we call unbalanced. We have the speed of the rotation of the fan. This is the operating speed. Uh, we have a damping coefficient for that particular problem. This is given to us, damping ratio actually, not damping coefficient, damping ratio. And we want to specify the springs for mountings, such that only 10% of the unbalanced force is transmitted to the ground. Now remember, 10% of the transmitted force means that Ft, big Ft over F naught is 10%. Now, because it's an unbalance here, you have to give meaningful interpretation to F naught, and that's going to be the mass times omega squared times eccentricity. Okay? Now, eccentricity is not given to us by itself, okay? But we're given the product of M by E by G. But of course, you divide it by G, you get the product of M by E. But anyway, let's go ahead and find out what we know. The 1000 RPM is that many radians per second. The mass is in the units of slinch. You take the pounds, 100 pounds divided by, if you wanted to get it in slugs, you divide it by 32.2. If you want to work with inches and things like that, divided by 32.2 times 12, which is 386. So it's that many slinch units of mass. Now, M naught E, M naught times E times G is 20. You're told that the unbalance is 20, which means M naught times E times G, this is G basically, in inch per second squared, is 20. So out of that, you get M naught times E. Okay? Now, let's go back to the formula for the rotating unbalance. So, oh yeah, okay. You can either write it like this, in terms of omega n, or you can say, okay, omega n is omega r over omega n, so omega n cancel, and you can write in terms of omega. These are saying the same thing, except that one of them has r squared here, and if that's the case, there's an omega n squared here. If you don't want to get rid, you want to get rid of this r squared as omega r over omega n quantity squared, then you can write it like that. This thing plays the role of our F naught. In other words, Ft over F naught is zero point 0.1. We already know that. Okay. So this thing, which is Ft over this guy, is 10%. So we know everything. The only thing that we know is R. Okay. So we find the R. Once we find the R, we can go and find the spring constant. Because omega n is omega r over r. Remember, r is omega r over omega n. I mean, you can write omega n equal to omega r over r. We know this number, 105, right there. We know the r, we just calculated it, 3.7. Square root of k over m. We know m, we just did it right. What is that, right here? 0.259 slinch. And I'll give you the value of k, which is this number, 210 pound per inch. This is wrong too, per inch. All right, not n, per inch. Okay, good. And that takes care of the problem. Oh, it also says find the transmitted force. If you want the transmitted force, okay, so you go to this expression. This thing was 10%, 0.1, right? What is that, 0.1? And everything else, this stuff is, you just write it down, m naught times E is 0.0518 right there. And omega R is 105, you square it. So basically that gives you Ft, which is 57 pounds. Good, that takes care of this problem. Let's go to problem 5. So we have a single cylinder engine here, and the concept of top dead center means where the piston reaches maximum height, the bottom dead center when the piston reaches its lowest height. Okay, and this is called stroke. Top dead center, bottom dead center, stroke, which basically it's twice the radius of the crank. Okay, so you can see that. So here's the problem: an engine weighing that many pounds is supported on mounts having a total stiffness of this and a damping ratio of 0.01. Basically, we're doing the mass spring damper system. So you're giving the stiffness, you're given estimated stiffness, estimated damping coefficient, and the mass of the object, the piston. Uh, Actually, sorry, this is the mass of this is the weight of the engine. It's not the piston. The weight of the piston, which is this piece, is only 20 pounds. The engine is 1,000 pounds. That makes sense because the engine is a lot heavier than this, okay? And it has a stroke of 9 inches. Stroke of 9 inches, okay? Stroke is the distance between the top dead center and bottom dead center. Now, we have the operating speed. We want to know the force transmitted to the support, okay? So when you look at this problem, it's the category 1 problem where you have a harmonic load, okay? You have a harmonic load specified, and we want to find the force transmitted, okay? So first thing that we're going to do, find the natural frequency of the system. When I say that system is mass of 2,000 pounds, of course, you have to convert it to slinch. You divide 386. The stiffness of the spring is given 20,000 pounds. So this is the natural frequency of the of this piston system. Okay, with that configuration, natural frequency is this. Uh, Not the piston, not the piston. Okay, it's for the engine. Engine. You're using the mass of the engine, not the piston. Okay, so we have the omega, which is 1500 RPM converted to radians per second. Now, out of that, we can find the R, 157 for omega, basically the rotation of the crank here, okay? And divided by natural frequency of the system, the engine is going to be, the ratio is going to be 1.786. And you go to the formula. Now remember, uh, you can view this, you can view this as a rotating, you can view this as a rotating unbalance. But let me put it this way. This whole thing can be viewed as F naught, okay? So, well, let's move on. So remember, there are two ways of writing these things, like that or like this, okay? We want to calculate F of t, the force transmitted to support. This is what we want to calculate. There is some stuff that we have, except that I am not given m naught or I'm given m naught. M naught is the mass of the piston, and this E is half the stroke. This eccentricity, this eccentricity is half the uh, stroke. Okay, so basically it's the radius of that radius of that crank. Okay, and we know the value of zeta, we know the value of r. So out of, when you plug it in, you're going to get the value of f of t. This is the crank speed, you know that. Okay, this is the mass of the piston. This is the half the stroke length. Okay, and you just plug it in, you're going to get 2747. Now, I want to go back here and just for a second point out to something, and that is, although that is not strictly correct, but what's happening is that it's pretending that the unbalanced mass, which is the mass of the piston, is kind of all put at this location, at the distance of half the stroke length from the center of rotation. So you can think about this thing. It looks like we're treating it like that, that the mass of the piston is presumed to be at this location, although the piston is up there. But the way this problem is solved, and you can solve problems like that this way, okay? Put the mass of the piston here. This is the half of the stroke distance, okay? And then just go ahead and solve the problem as a rotating unbalance, okay? Uh, yeah, so somebody actually could have given us m naught times E, okay? And then, we would have solved the problem the same way, except that uh, I'm telling you that for a problem which involves the motion of a single cylinder engine, this is one way of solving the problem. Treat it as a rotating unbalanced problem where you place the mass of the piston at a distance which is half the uh, stroke distance. Okay, solved as a rotating unbalanced problem. Okay, this is what you saw because you backed up. Now, problem number 5. Uh, well, let's see. A machine, 100 kilogram mass, so this whole shebang, this M is 100 kilogram. It's sitting on a spring of total stiffness of 700 kilonewton per meter, and has an unbalanced rotating element, which results in a disturbing force of 350 newton at that speed. Notice that here we are not given the value of m naught. We are not given the eccentricity. What we are told is that whatever this thing is doing, and that is causing a vertical oscillation, is going to give you a harmonic load of magnitude 350 newton, amplitude 350 newton. Okay? So, although it is a rotating unbalanced problem, but I'm not going to solve it like that. I solve it as category one problem, and uh, basically the one that's at the right hand side is F naught cos omega t. Okay. What do we want here? We want the amplitude of the motion due to unbalance, which means the big X. We want the big X, and then the transmissibility, obviously force transmissibility to the ground, and the transmitted force. So let's go ahead and see. This is the uh, this is the RPM of the engine. Well, the engine, I mean this thing that turns. That's what I mean. And this thing is your F naught, which really is coming from an unbalanced source, mass unbalanced source, but the way it's all bundled up and given to us is that it says this guy is 350. That's why they're not giving specifically what the mass unbalance is or what the eccentricity is. They lump it together and say this fellow is your F naught and it's 350. Not enough information given to do it like this, okay, like that. We can do it like the one on the left, but not the one on the right, okay? So first thing that we need in these problems, you need R. Remember, you need R, so you have to find the natural frequency. The system spring stiffness is given as 700 kilonewton, and the mass of the machine, this whole thing, is 100 kilogram. Just plug it in, you get your radians per second. This is your R, not R, omega R, that's what I mean, or omega, drop the R, okay? So work it out. So you have R is the ratio of these two, 3.754. Now you go to the formula, which gives you the amplitude of oscillation under a harmonic load, right there. Now you might say, wait a minute, what about the M naught E? Well, the M naught E, remember M naught E times omega R squared is given to me. M naught E times omega R squared is that 350. Okay, so although it appears here, but it's kind of a, uh, you know, uh, unnecessary to write it like that. Okay, but if you want, we can do that. This is M naught E omega R squared. That is your F naught essentially. And then this denominator, if you look at R squared here, for example, if you look at R squared, this is omega R over omega N, right? You square it and you get this. This is given to us. This is your 350. And this is your stiffness, mass stiffness. So when you think about it, although I've used this formula, but essentially this formula could have been viewed as big X equal to F naught over K times that dynamic magnification factor, okay? So you can look at this as F naught over K times that, category one problem, and we want to find the X. So written like this. This is 350. K is given to you, or we calculated, and zeta we are given. I believe, let me see now, is zeta given here? Let me back up for a second. Is zeta given? Yeah, 0.2, right there. Okay, so let's go here. And we want to calculate big F of t. Okay, that's what we want to calculate. 350, this is 350. Well, first of all, part A says find the amplitude, big X, and we do that. Everything you know on the right-hand side, plugged in. And part B, it says find the transmitted force, right? So write down the expression for the transmitted force from category one problems. Remember, when I say category one problem, I'm talking about chapter 2. First problem. Second problem was base excitation, which was built on the first problem. Third problem was rotating unbalance, which is also based on the first problem. So the first problem was mass spring damper system under harmonic load. That's what I mean. This comes from that category one in chapter 2. So Uh, we are asked to find the transmissibility, which is this, and in part C it says what is the actual force. So transmissibility, force transmissibility, obviously, is this thing. Just plug it in. Uh, uh, this thing can be calculated. We have everything here. We have zeta, we have r, and once we get that, we just multiply it by this number, which is your 350 pound, and you're going to get force transmitted. So the force transmissibility is that ratio, just worked out. Part C is just taking that F naught, which is 350 times this transmissibility, and you're gonna get the force transmitted to the ground due to this rotating unbalanced problem. Okay, unbalanced machine transfers that much force to the ground, and if this is too big, it's gonna go through the ground to some other location. Maybe another instrument is sitting there and can damage that. And that takes care of the problems that I wanted to do for review today. Good luck for your test number 3. Please come 5 minutes earlier, and because you have 16 minutes altogether, uh, we have to be out of the classroom at 4 o'clock sharp because there is another midterm coming in at that time. 20 multiple choice question, each worth 1 point, no part marks, and one problem to do. It can be a rotating unbalance, it could be a base excitation, and it could be a generic category 1 problem. And that's pretty much it. All right, good luck.